Okay, good afternoon, everyone. I hope you're doing great. Before anything, please get to the call app, and if you go to the course content that I have provided for you, um, please go to the content. The last folder would be today's content. There are two files. One is chapter 5A, and the other one is chapter 5B, trying on a short data set. So for now, please download this one and drag and drop this to Colab. So yesterday I told the friends who were in the class to upload the Kaggle dataset if you haven't already done that. This is the last file, the Kaggle original data. You need to download that file, extract it on your computer. And after that, if I go to Google Drive, click on My Drive. So definitely, if you have gone to Colab, you should have something like Colab Notebooks. Inside there, I created a folder called Chapter 5. Make sure that you're going to use exactly the same name. So I type it again for people who are in the Zoom session. Make sure that you have this folder. Also, the other folder that we need to have is this one. So inside there, let me just get rid of this folder. I'm gonna delete the one that I created in the previous lab because we're going to create everything from the scratch. So if you already created that folder, you need to either drag and drop the Kaggle dataset. If you see, I have provided a dataset here, whether you have to drag and drop, say Control A, for example, drag and drop everything over there, or the other possibility would be you right click on an empty part and say file upload, and then go to this folder and say Control A and then open. So it's going to upload all the files into Kaggle original data. It's a kind of time-consuming process. If you already have that, means if you click on Drive, Note, Colab Notebooks, and Chapter 5, if you have already the original data there and you have the files, please type 1. Guys, do you have that at home? If not, please go through the process. So Stefan has that. How about the rest? People in the class, guys, do you have that folder already filled with 4,000? Yep. if you go to the last 2 days contents, Kaggle original data, you can find it there. Okay. So I'm gonna tell one at a time. Okay, I repeat it again. Right now, we just work on this one, but in any step, I'm gonna tell you what to do. So first, make sure that you have Kaggle original data. Whenever you have all the data in there, I know that people at home, 2 of them are, it's going to take something like 45 minutes to copy all those files. Meanwhile, we are gonna do some other stuff, so don't worry. We are gonna use our time. Just people in here, do you have the 4,000 files already? Divine, it's copying. So you have it? You don't have it? Okay, how about you? You have it in the downloading? Okay. Look, the next part is going to this be, I intentionally, to ease the job for you, I have split it into different parts. If you click on this part, first you need to import OS and shuttle. Let's just download these two. It's going to ask without GPU, so don't worry about that. Then, guys, you need to have from Google Colab imports Drive, and then mount to Google Drive. Look at this part. Everybody could have different folders. This is kind of tricky part. Many people had problem. Make sure that this link is valid on your computer. For understanding if it is valid, simply you can go to your Google Drive. It starts from here. Make sure that you have Colab notebooks, you have chapter 5 already created, and then Kaggle original data. If it is something different at your computer, don't worry, you just need to change this part. Okay? The other thing is, this is the file, this is the folder that we are going to classify our data into training and testing and validation folders. This is not going to be a time-consuming part, so everybody for now, go to this and base directory, run that, and say make directory. Look at this one. I created a dummy folder just to show you how it works. So it is going to make a directory. Look at here, I don't have anything in my Google Drive with that name. Look at here, I don't have any mini test cat and dog small. When I run that line and I get back here, it takes 2-3 seconds and it shows that a folder is created. If it doesn't, simply just right click and say refresh. So it's going to refresh and show you that mini test. But go inside mini test and see there is nothing inside that. Okay, should I wait or everything is? Because you just need to drag and drop, the rest is following this instruction. did you upload the file? So it is working? Okay, this one, this file number B. This one, B. Did you download it? Is it in here on Colab?
Yeah.
So did you run the first? Rachel, did you copy these two? Extra folder? Okay, so it works. Or not. So just simply Control A, move to the other folder, right? Another way you can just rename the folder, then you don't have duplicated, and just move the entire folder. You can do that. Okay, so look, the next part is what is happening here? What is the base directory? The base directory is this one, mini test cat and dog small, right, Mahir? This is the base directory. What is happening in this line? Anybody can tell? No, we are going to have base directory, which is this one, everything from the scratch all the way to this. And we are going to say, let's have the /train. Okay, this is going to be the directory, but next line, we are going to create that train directory. Look, if I go to this one, now it takes a few seconds. I wait, and then it shows that the train is already created. How about this one? We do the same thing for validation. I just quickly go through validation and test. Look at the result here. I don't touch anything. It's already created, so it shows validation. And after that, test is going to get created. Do you see that? No? Yes? Maybe? Okay. People at home, can you please confirm if you can see such a thing on your computer? Okay. Take the time to create. So test is created too. So let's go, don't worry about error message. Go to the next. How about the Kaggle? How many photos do you have in Kaggle? Yeah. 44 minutes left. Okay. So I want. So everything is working or not yet? Okay. So guys, the only in the previous class we had almost most of the people that they had already the files uploaded. My suggestion is I'm going to go through the comments and just watch it at your convenience, the recorded session, and do it. Otherwise, it's going to be a boring video when you want to watch. So the next part is after creating all those folders, to create subfolders like inside train, I'm going to make cat and dog folders inside training. So if I go inside the train, it shows that cat and after a second, dog folders are already there, created. And I'm gonna do the same inside. Oh, I didn't make the dog. I'm going to do the same for cats and dogs inside validation and cats and dogs inside test. So what I did, I'm gonna upload the updated version. What I did here, instead of 1000 file, I just said copy the first 10 files because this is just a test. I want to show you how it works. I copy the first 10 files of the cat into the train cat folder. How it works, it says that cat dot curly braces dot jpg. What is that curly braces for? It's going to get filled with format I, and I is in the range of 10, means that it's going to be 0, 1, 2, 3, all the way to 9. The result would be cat.0.jpg all the way to cat.9.jpg in this toy example. And I'm gonna say for every single file inside file names, then we say the source is the original data set directory, that Kaggle data set. Get the file from there and copy it to this. In other words, paste it to this. Look how much time it takes. It takes almost a couple of seconds, but imagine that when it is 100 times more, it's going to be a quite cumbersome process for. So the next is copying. Technically, it should be 5. I copy 5 cats to validation, and I copy another 5 cats to test. And look at this one. The next part is going to be dogs. 1000. I should change it to 10. 10 dogs, and then 5 dogs to training, 5 dogs to, sorry, 5 dogs to validation, 5 dogs to testing. I just use 1% of the original size to show you how it works. For the sanity, if I check, it shows 10 images copied into training, 10 other images from dogs copied into training. Now 5 cats in validation, 5 dogs in validation, also 5 cats in test, and 5 dogs in test.
Those temperatures randomly?
No. I'm gonna tell you why not. We have, okay, wait a second, because it goes back to this line, Nigim. This line, it's not random. We pick first all the way to 9, right? So we have 2,000 cats, 2,000 dogs. We need to pick some cats, some dogs. It cannot be generated random. We need to say which files we want to have. I'm gonna explain exactly that one in this. I just want to make sure if more people could finish this. How many of you?
like, I don't have some of the cat, so it gives an error.
Okay, just
That's why I asked if we can fix that.
um
One later, I think it's worth like.
okay, so the good thing is because we have some other task to do, till the first, until that we are going to have the first break, most of the things are gonna be done in all the computers. So especially I'm gonna give a kind of lengthier break to make sure that everybody could go through the steps. So guys, look at this one in the other collab, please everybody upload chapter 05-A, this one, the first file. Now please upload that. Okay. And in the first collab that I showed you how to go through, and let me show you what happened inside I created for you this mini test, and I copied files into that. So you remember we created these 3 folders, right? And inside train, for example, we had cats and dogs folders. Look at this one. Inside cats, we have cats from 0 all the way to 9. Huh? And in dogs, we have the same thing, dogs from 0 to 9. If you go in test, you see in each folder, we have just 5 cats and 5 dogs. I have done that in I'm going to open another file, Control O, upload. There is another file that I provided for you, and that is chapter 5C check. Instead of B, replace it with file C, upload C in there, please. Okay, so technically you should have just A and C, right?
In chapter 5 folder.
In here, A, B, and C, download these 2, okay, then. And now you see that we have 2 collab. Do you see A here and C here? We just need to have these 2. Okay. I provided this partition for the chapter. If you click on that, it's going to collapse all the commands that we covered in the previous sessions. So you don't need to go there. And you should see 522. Everybody could confirm that you can see 522. This one at your computer. No? Maher, is this file chapter 5A? Okay, scroll down. You should get to a place that it is 522 downloading files, or page 132. Search for this. Control F, 132. You got it? You got it? Awesome. So if you have already created all the folders, and if you have uploaded, if you haven't uploaded yet, so please don't copy this, but don't go to the copy part. Run all these cells if you have already uploaded all the files in the original Kaggle data folder. It is going to ask you to pick a user that you want to use for the sake of Colab as well as the Google Drive. So I've chosen another user to make sure that everything starts from the scratch and I'm on the same boat. And we do not rely on the data that I have uploaded previously. So it's brand new. I just copied all the data yesterday. I say the original data set is that Kaggle original data. We are supposed to have all the files over there, those 4,000. And then this is the actual folder, cats and dogs, guys. We are talking about these cats and dogs that we are going to create because you haven't done. Let me just delete the mini test. So suppose that you don't have this on your Google Drive. We want to create them. What we are going to do, we say, hey, go to Colab, to chapter 5, and then this is the folder cats and dogs small. I shouldn't do that because it's going to give me error. I already have it. If you don't have, you need to click to run this one. It's going to create that folder for you. Please try it. Does it work? It should work without having data. Does it work? Could you check at the same time your Google Drive? No, this one doesn't have anything to do with. It has nothing to do with uploading. Now we just create empty folders, okay? And meanwhile, good portion of the data would be already copied. So the next, the same as what we did a few seconds ago, create train. I'm sorry. You see that I intentionally said create the same folder and it gives me error because I already have that. So I should be careful. Please go through all these folders and create them. I need to have them not to copy or do anything. I need to have them to check if I have correct number of pictures in each folder. Whenever you are done with creating all those folders, please go and check in the Google Drive. You should have a structure like this, cat and dog small. You should have test train validation. Inside test, you should have cats and dogs. The same in train, the same in validation. Okay? So take your time. And whenever you see the same set of folders, please give me a signal. Done. Now, your question, Negin, that the files, random files. We have cat dot something here, JPG, and then we say dot format I. Look at I. I is the range of what? 0 to 10, not including 10. So if I show you n frames, f names is going to be cat0 JPEG, cat1 JPEG, and so on and so forth. What if I change the range from 10 to 20? It's going to be cat.10.jpg all the way to 19. Does that make sense? Rachel, does it work? Sorry? Under cats and dogs, where? Sorry? Okay, I'm gonna check what's line. So you should go back to that. Go to any of them. In any of them, you should have cat and dogs. Okay. You haven't run the. So how many minutes still you have thinking? It should, if you go to. Doesn't tell you?
But I don't have all the information.
I know. So it was 44. Now it should be like 20 more minutes. Okay, for those who have the files already, what this command would do, this command would take the first 1,000 cats from index 0 all the way to index 999 and copy it from the source Kaggle dataset into the train cat directory. Then we are going to take the next 500 cats and place them into validation cat directory. And then we are going to take the last 500 and place it into test cat directory. Because I have already done that, if I go, for instance, to train and I go to cat, I see that I have 0 all the way. If I go, it takes, but I have 1,000 cats here. And the same applies to dog. For the validation and test, look at the validation index that I start the cats. The validation starts from 1,000 and then 1,001 and so on and so forth. So after finishing all these lines, then do you see that it says as a sanity check, let's count how many pictures are in the training split. Do you see that, Rachel? This one. It takes almost 1 hour from now to, if you haven't done the upload or something, to get to this. So it's going to show you we have 1,000 cat pictures, 1,000 dog pictures, 500, 500, 500, and 500. Okay. But did you see that, guys? I have done this job 100 times, but unintentionally I clicked and I said make directory. The directory is already there. To eliminate this problem, I created for you that chapter 5C just to check. And you're going to see I classified the hands-on into separate portions. If you go there, I just say import OS. I mounted the drive, Google Drive. These are the things that we need to have. And after that, simply, I just said, take the cat and dog base folder, and then I said, join train validation and test. And then I said, go to train directory, cats and dogs for validation, cats and dogs for test. And now look at this one, just in a fraction of a minute, I could go through all the folders to make sure that first, all the folders are there and correct number of samples are already created there. Did you understand why I created A, B, and C? So in short, A is following the instructions of the book. B is a kind of miniature version of copying files. Just it takes 1 minute to show you how the mechanism works. And C is for just sanity check to see if the folders are there and the correct number of pictures are already uploaded and copied. The reason for that is from that moment, we start working with all these pictures. So we need to make sure that the foundation is correct. Okay. So meanwhile that you try to copy all those things, let me share with you the shape of the videos that I planned to see in these moments that we cannot do anything better.
Convolutional neural network. Well, let's start with the basics. A convolutional neural network is a type of neural network that is most often applied to image processing problems. You've probably seen them in action anywhere a computer is identifying objects in an image. But you can also use convolutional neural networks in natural language processing projects too. The fact that they are useful for these fast-growing areas is one of the main reasons they're so important in deep learning and artificial intelligence today. Once you understand how a convolutional neural network works and what makes it unique from other neural networks, you can see why they're so effective for processing and classifying images. But let's first take a regular neural network. A regular neural network has an input layer, hidden layers, and an output layer. The input layer accepts inputs in different forms, while the hidden layers perform calculations on these inputs. The output layer then delivers the outcome of the calculations and extractions. Each of these layers contain neurons that are connected to neurons in the previous layer, and each neuron has its own weight. This means you aren't making any assumptions about the data being fed into the network. Great news, but not if you're working with images or language. Convolutional neural networks work differently, as they treat data as spatial. Instead of neurons being connected to every neuron in the previous layer, they are instead only connected to neurons close to it and all have the same weight. This simplification in the connections means the network upholds the spatial aspect of the data set. It means your network doesn't think an eye is all over the image. The word convolutional refers to the filtering process that happens in this type of network. Think of it this way. An image is complex. A convolutional neural network simplifies it so it can be better processed and understood. Let's look now at what's inside a convolutional neural network. Like a normal neural network, a convolutional neural network is made up of multiple layers. There are a couple of layers that make it unique: the convolutional layer and the pooling layer. However, like other neural networks, It will also have a ReLU, or rectified linear unit layer, and a fully connected layer. The ReLU layer acts as an activation function, ensuring nonlinearity as the data moves through each layer in the network. Without it, the data being fed into each layer would lose the dimensionality that we want to maintain. The fully connected layer, meanwhile, allows you to perform classification on your data set. The convolutional layer is the most important, so let's start there. It works by placing a filter over an array of image pixels. This then
You remember this? What is this phase?
the convolutional
What do we call this part? Remember? It is the conv2D part. What is the frame size in here? The frame size of the conv2D. 3 by 3. Look at this one.
Oh, yeah.
layer
3 by 3. We have two things here. One is stride, and the other one is valid or save. What are those parameters, if you recall?
So basically the column, so it's goes one column to the right and to the next. And
How many by how many?
So
That's exactly. What is the stride here? Lovely. 1. What is the other one? The valid and save. They same size. Which one and which one? When the output of this convolution has the same size, we call it same. When the size is reduced, as you see, it is reduced actually, we call it valid. What is the default? Valid. Okay. So awesome.
let's start there. It works by placing a filter over an array of image pixels. This then creates what's called a convolved feature map. It's a bit like looking at it.
So the book said,
allows you to see specific features.
well, he said convolved feature map, but this is the feature map. What is this one? This is the output feature map, right? And this output feature map is a feature map for another layer. And that would be the output feature map of this one. So we go there. What is the role of convolution if somebody asks you? It's a good thing. So if you have a chance to work on, I have to be close to microphone. Did you have a chance to work on assignment number 3? Not yet. Okay. So that's the intention. Actually, there is one video, a convolutional neural nets. It's 23 minutes. We don't have time to watch it here. And it talks extensively about the assignment number 3. You know that it applies different filters. You remember you asked, oh, you didn't ask. The other person asked. What is that 32 in conv2D, for instance, when we have 32 comma 3 by 3? What is that 32? Number of filters that we are going to apply. It could be 32, it could be 64. Is it predefined set of filters, or we pick randomly filters? Means that the 32 filters, there are going to be always those 32 filters in this computer and the other computer, or no? We have set of filters. Imagine that we have hundreds of filters, but we are going to pick 32 random filters among the filter set that we have. Does that make sense? Okay. Again, my question, what is the role of kernel and convolution conv2d?
Basically having some filters to the like the data or like the image that you have, and using those filters you can identify some specific details in the image, so it's going to be better for vision view.
It's going to intensify some of the features and eliminate the other, or lower down the importance of some others. Let's see.
You might not otherwise be able to see. Next, we have the pooling layer. This downsamples or reduces the sample size of a particular feature.
What is the usage of a max pooling? It already said. One of them is downsampling, but is it the only thing that we have? Downsampling? Again, to intensify that, okay, I'm searching for instance, vertical lines or horizontal lines, and I want to emphasize on them. So get the maximum value in each square for values, right? What is the default window size? Max pooling, what is the default window size for that? For conv2d, mostly we use 3 by 3 or 5 by 5. 2 by 2. What is the stride? Exactly. Everything is 2 in max pooling 2, right? 2 stride, 2 by 2. Excellent. So if somebody asks you conv2d max pooling, now what do you say? Conv2d is responsible to apply filters and extract the output and intensifying on some of the features like vertical line, horizontal line, diagonal lines, curves, and so on. And max pooling is responsible to reduce the size as well as, means downsampling, as well as making those features more vivid, right? To intensify those features. Okay.
Makes processing much faster as it reduces the number of parameters the network needs to process. The output of this is a pooled feature map. There are 2 ways of doing this: max pooling, which takes the maximum input of a particular convolved feature, or average pooling, which simply takes the average. These steps amount to feature extraction, whereby the network builds up a picture of the image data according to its own mathematical rules. If you want to perform classification, you'll need to move into the fully connected layer. To do this, you'll need to flatten things out. Remember, a neural network with a more complex set of connections can only process linear data. There are a number of ways you can train a convolutional neural network. If you're working with unlabeled data, you can use unsupervised learning methods. One of the best popular ways of doing this is using autoencoders. This allows you to squeeze data in a space with low dimensions, performing calculations in the first part of the convolutional neural network. Once this is done, you'll then need to reconstruct with additional layers that upsample the data you have. Another option is to use generative adversarial networks, or GANs. With a GAN, you train 2 networks. The first gives you artificial data samples that should resemble data in the training set, while the second is a discriminative network. It should distinguish between the artificial and the true model. A lot of people seem to be asking what the difference is between a convolutional neural network and a recurrent network. It's actually quite simple. Whereas a convolutional neural network is a feed-forward network that filters spatial data, a recurrent neural network, as the name implies, feeds data back into itself. From this perspective, recurrent neural networks are better suited to sequential data. Think of it like this: a convolutional network is able to perceive patterns across space. A recurrent neural network can see them over time. If you want to get started with convolutional neural networks, Python and TensorFlow are great tools to begin with.
Okay. How far could you get, guys? The copy is done. Already. Good. So before we go to the break, designing the way that before we go to the break, hopefully you're already done by uploading all the files. Apart from it, I'm gonna tell you what to do. So when we come back from the break, good part of it is already done, so you can continue. So let me just see if I copied the correct file. Yes. Stefan, yes. I hope that if you have already uploaded all the files, so let me just answer the question to Stefan. I hope that you can go through all these parts so they can copy the file from the original Kaggle data set into all those folders. So if you start doing it, just run all those cells. It takes quite a while, and stop at before 523, building your network. Yes, you see that I think that if you started at 1233, you should already be in the dog copying part, I guess. Thanks for asking anyway. Let's go to
that images. Have you ever thought about how the computer is capable of doing this? Well, I did every single day until I figured it out. Today, I will visualize the process for you step by step. Let's have a look at the model we're going to visualize. This is the pre-trained model that has an accuracy of 95.4%. A quick note before we move on. This video is strictly visualization. I will be making a separate video with everything explained in detail. Stay tuned for that one. Now, let's have a look at all the layers before we start. We'll input images from an M-list dataset. This is a dataset consisting of handwritten digits from 0 to 9. After inputting the image, we will perform convolution. We'll use two filters, or kernels as they're called, that have the dimensions 5 by 5 by 1. The activation function, denoted as A, is relative. Next, we'll perform max pooling with a pool size 2 by 2 and a stride 2. This is our first layer. Then we move on by performing our second convolution. This time, we'll use 4 filters that have the dimensions 3 by 3 by 2. The activation is sigmoid. We'll then perform max pooling exactly as earlier before we flatten the matrices out. This gives us a flattened layer with 100 nodes. Here is our second layer. Finally, we have a fully connected dense layer which outputs our predictions.
Guys, do you see that here we have all these convolutional neural nets, and what is this one? The traditional densely connected layers that we know as hidden layers. So technically, we have conv2D, and normal conv2D has this problem that we need lots of pictures not to get to overfitting, and we have a general idea of what is happening. Does that make sense? If you use just this architecture and you go to the hidden layer, what would happen?
More accuracy?
instead of, yes, if the question is compared to just only having hidden layers, the answer is correct. We are going to have more accurate mechanism, but we are talking about the overfitting. Convolutional neural nets brings us suddenly to overfitting. It's going to make the model very much biased towards the data that they have in hand, and it cannot be very much general. So what should we do not to go to that road? This is the whole idea of this session and today's class is this, to see the problems and to prohibit that. Let's see.
Is any more time? Let's see the model in action. We start with the input layer, which is a 28 by 28 by 1-dimensional grayscale image. The image is fed into the first convolutional layer that consists of 2 5 by 5 by 1-dimensional filters. And
Guys, normally, what is the filter size that we use? And in your assignment, 3 by 3. So this gentleman used a kind of, and the very first time that they used conv2D, and when we say the very first time, it sounds like 100 years ago. It was 12 years ago. They used 11 by 11 for the first layer. And right after that, next year in 2013, they used 7 by 7. And after that, they got to have just this tendency to have 5 by 5 for the first conv2D and 3 by 3 for the rest. Does that make sense? But in many cases today, I don't see that they use different frame size for the first conv2D and the next. Some people, many people, use 3 by 3 from the start till the end. Does that make sense? Huh? But look at the result. Because we have 5 by 5, the slide size was what? 28 by 28. Instead of 26 by 26, it turned out to have 24 by 24. So you see the size reduced by the factor of
2 biases, 1 for each filter. We'll use the sprite of 1 and an activation function called relative. We start with the first filter and map the activations onto activation 1 in the first layer. Then we do the exact same thing for the second filter and map the output onto activation 2 in the first layer and move on.
Okay, what do you see from this? Isn't it beautiful? If I have one diagonal, so the gentleman didn't try all the possible filters. He knew what he wanted. So he wanted to have a filter that could recognize diagonal lines and horizontal lines, right?
As you can see, the first convolution outputs 2 different images or matrices. These are called channels. Next up is the max pooling.
The channel is the output that we have after applying filters. Channels in hidden layers meant just colors. We had 3 channels RGB. We had 1 channels grayscale. But here channels means the output of the filters.
The pool size of 2 by 2 and the stride 2. We run the pooling for each of the channels and output them respectively.
What I don't like about this visualization, that's the only comment that I have, is if it wants to show the real kind of implementation, you should just consider the size of this should be half of this size. You see, the squares are way bigger than their original size. So this one should be small size and intensifying the feature.
Yeah, so we want to extract only the most activated pixels from the first convolution and shrink the dimensions As you can see, we have shrunk the dimensions from 24 by 24 by 2 into 12 by 12 by 2. Have a go and count the pixels if you'd like to. Next is the second convolutional layer. Here, we'll use 4 filters with a square one and an aggregation function called sigmoid. As you probably noticed by now, these filters are stacked, and if you separate them, you'll see that we actually have 8 filters. So, what's going on? Well, there are 4 filters with the dimensions 3 by 3 by 2. Since we have 2 channels from the previous activations, we'll have 2 channels in each filter. In addition, we also have 1 bias for each filter. Running the convolution will return 4 outputs, 1 for each filter. As you can see, we kind of lose the idea of what the original image was. From this point on, it's hard to decode what is actually going on. But let's continue to the last max pooling. We'll do exactly as we did earlier. Since there are 4 channels, we'll output 4 channels. What we extract is the most activated pixel values from each channel. We'll then take these 4 matrices, flatten them out, so that we separate each and every pixel. We went from 4 matrices that were 5 by 5 to 1 flat layer with 100 nodes. To make the visualization easier, we'll shrink the nodes so that we only see the first 5 and 5 last nodes. Finally, we have the output layer where we want to output 1 out of 10 different predictions. This is a fully connected dense layer. Running the activations from the 100 nodes, we see that the model predicts that the inputted number is 7. This is exactly what my brain told me as well. Crazy, isn't it? Stay tuned for the next video where I will show you all the steps in detail.
Okay, can you please give me a kind of estimation? How many images already on? Sorry, you copied as well? The copies, how about you? Okay, how about you, Nigel? The copy. So those who are done, just let me tell. In A, after you are done with copying, did you create all the folders as well? Okay, do you see these explanation? I said a quick explanation. After that, you're going to copy the files. If you are done, go right after that, Negin, and start running all these all the way to this part to check sanity, and don't go further. Stop there. Okay? I mean, just like this. Run, shift, tab, shift command, and then go all the way. You had a question.
So I think it was lost in the video when we went for the second convo. The images were like kind of showing
Kind of adding them together,
Yeah,
kind of
so
thing. It's a
wasn't able to like say it's silly. Because like the images like that we got wasn't like that much clear to you. Yeah.
there is one factor. And even not next week, but a week after that, we are going to get to answer this. But I quickly go through it just to show you that we have the answer in future. Do you see this? Imagine that I have a picture of cats like this one. I apply a filter and it's going to bring the result like this. Do you remember that I said we are going to apply, for instance, 32 filters? The result of those 32 filters would be something like that. And we are going to have more advanced, more complex filters. We get this one, and then we are going to apply those filters onto just this, and then we are going to apply onto this and to this and so on and so forth. Does that make sense? Remember, computer is not human. It's not going to find that, oh, I found a beautiful cat here, so it is cat. It needs to find some elements that it can recognize, computer can recognize, not us, that we say, oh, we don't see any 7 there. Exactly, if you see something like this, you are going to freak out if I tell you that, what is this? You know, I don't know, is it kind of ghost or something? But this is going to help computer to go towards recognizing those who have these thingies, apparently ears of cats. Does that make sense? And the reason that we don't have very much picture here, result here, do you know why? Because we have that much fine sieve that you cannot go through it. You know, in the first layer, the granularity, I could say it finally, the granularity of the sieve is super big, so everything could get through and you have the output of the picture. Does that make sense? But here we have that much fine sieve that not everything can get through, and we have limited outputs. But definitely if you have these things as the output, then we have a cat. That's a very top level answer to your question. We are going to get deeper into that, but already the whole idea is just applying those filters. Okay. To let you know which pages we have gone through, we went through creating all these directories and we went to copy all those things. So technically, after sanity check, you're done with everything all the way to the beginning of 523. So I want to make sure that majority of people would get to this part. So let me show you another video, which is fantastic. And then we are going to, let me just first. This is awesome.
To support the production of more high-quality content, consider supporting us on Patreon or YouTube membership. Additionally, consider visiting our parent company, Earth1, for sustainable living made simple. Throughout this deep learning series, we have gone from the origins of the field and how the structure of the artificial neural network was conceived to working through an intuitive example, covering the main aspects and some of the many complexities of deep learning. Now, all these videos have only been focused on one type of neural network, the feed-forward network. The focus of this video then will be to initiate discussion on another very popular and important neural network architecture, the convolutional neural network. For our discussion on convolutional neural networks, we will go with a very common example, number recognition. The reason this example was chosen is because of this great interactive resource by Adam Harley.
Who is the gentleman? Adam Harley was my classmate at Ryerson, TMU. Adam Harley. And he is, I'm telling you, we had one course together with Dr. McHenry. Adam was the son of another prof at Ryerson, Dr. Eric Harley. Very tough prof. It is recorded. Okay. And very nice prof at the same. So Adam was he implemented this that you see by just using C programming language. I mean, just everything from the scratch. And he didn't use, the funny part is he didn't use any back then deep learning, machine learning, and so on. So it was like creating, inventing everything. And I remember that he just managed changing the handwritten digit, and it shows that the percentage on the other side, the percentage of the chance of being 1 or 7. So especially when he just wrote 7 and 1, the chance was very similar for those two numbers. And I've paused here to show you one thing. This is the MNIST kind of thing here. You see that? Look, the very first layer we apply for people at home, for the very first layer, we apply conv 2D, and you see a tiny, teeny reduction in size happens. You see that? So it is almost, for instance, 28 by 28. It is 26 by 26. You have to be very, I mean, just meticulous to count the numbers. But I very much like this conversion. This is max pooling. The size of this vividly is half the size of this one, right? In both dimensions. And look at the other one. Now, whatever it is, you apply another conv to the, so it's going to be more number of filters applied, right? And more strange, kind of stranger for us. And again, what is this layer? Can you tell me? Another max filling, lovely. So you see that here we have smaller but sharper kind of picture. It tells us what is the feature that is very bold in here, and so on and so forth. Does that make sense? And look at this. At the end, you have that. So let's just flatten them and make it that. And then you're going to just make it like the first input layer for the hidden layer. What I very much like about this 10-minute video, 10 minutes, yeah, is this scene. It is the anatomy of convolutional neural nets, all in one shot. Can you feel it? We are going to do the flattening layer, right? So imagine that this is the flattening, and then that one is the hidden layer. And the one at the end shows that the chance of being one, so who's responsible for that? Softmax. You say, hey, this one has the higher chance, right?
Audit's PhD at Carnegie Mellon University. I have linked the resource in the description so that you too can experiment with it and see the internals of a convolutional network. Now, if you can recall from our example on an image pattern recognizer using a feed-forward network, we set up an idealized system and made the assumption that each hidden layer in our network would build upon further layers of abstraction, from vertical lines to combinations of vertical lines. However, in actuality, as we explained, this wouldn't happen, and the receptive fields of the network would be a lot more random to the human eye due to the architecture of feed-forward networks and how they compute. With convolutional networks, however, this isn't.
Look at this one.
Feed-forward networks and how they compute.
Look at this one. This is super strange, how computer can understand anything out of it. But remember, that's the task of computer. So don't worry about computer. Our problem is we say that I can't see any rabbit in the picture. We can't, right? But computer can.
Networks, however, this isn't the case, and we could to some extent see these layers of abstraction building up. Before we delve into why and how this happens, let's first set up a structure for the network we will be using.
Another thing, do you see that this is low-level features? It's not complex at all, so they are not complex. But one level towards.
Before we delve into why and how this happens, let's first.
Do you see that it says that mid-level features? We have more shapes, right? That can you detect any ear in the? Can you detect any nose in the? It really depends on. And we go further.
The structure for the network we will be using. As with our previous example in image recognition, the input will be the individual pixels of our image, and the output the patterns we are trying to classify. In this example's case, we have 10 outputs, numbers 0 to 9. For the layers in between, we will have 2 convolutional layers, 2 pooling layers, and 2 fully connected layers. Now, that was a lot of new terminology thrown around, so let's break it down layer by layer, starting with the input. While we have already stated that the input is the individual pixels of the image, I want to mention some important details about how a computer views this image. Every image in a digital device is stored as a matrix of pixel values. This is referred to as a channel, a certain component of an image. Now, with a typical digital camera, every image will have three channels, red, green, and blue, RGB, which you can imagine as three 2D matrices stacked upon one another. For the sake of simplicity, we will assume our input has just one channel, the luminance of the image, with the value of each pixel represented in 8 bits. In other words, the pixel values will range from 0 to 255, with 0 indicating dark or transparent luminance, and 255 is bright. As a side note, digital systems store all types of sensor data and other information in this fashion. For example, for a convolutional network that would operate on speech, we could represent that speech as a matrix of frequency values. Coming back on topic, now that we understand the format of an input, let's finally delve into where the real magic happens, the convolutional layer. As you can assume, this layer and the network as a whole get their names from the convolutional operator, which in layman terms is a mathematical combination, in other words, the dot product of two functions to produce a third function. In CNNs, this operation is implemented in what is referred to as a feature detector, filter, or most commonly, a kernel. You can think of a kernel as a mini matrix, orders of magnitude smaller than the input. In a convolution operation, then, the kernel moves across the input image, taking the dot product of the two matrices, and then saving the values to a new matrix, dubbed the feature map of the original image. At this point, you may be wondering how this is able to detect any features at all. Well, if a kernel is initialized with the values in a specific configuration, they can be used to transform an input image and find various patterns. Take these kernels, for instance. When loaded with the appropriate values and convolved with the input image, produces an output which highlights various edges in the photo. Now, I won't delve into the specifics of the various types.
Guys, this is exactly assignment 3. Okay. You're going to have one picture and you're going to apply. And honestly, the time that I designed that, I started, just applying different filters. I was like, wow, let's just change these numbers and see what's going to happen. And I was very surprised. Like some of them, it's like you have a picture and you convert it to like, what do we call it? Using pencil, black pencil kind of drawing. Just applying a simple filter. I didn't know how I made that, but it just turns to be like a sketch of handwritten things.
Terms of this video, but there are many resources that talk about them extensively, such as Computer File and their various videos on kernels like the Solo Edge Detector. Coming back on topic, as you can see, kernels are essentially ways to do fast computation and produce a new output. In this case, we're doing it with an image, with an effect or features highlighted. Programs like Photoshop use these simple kernels for effects like blurs, for instance. Now, when we look at a typical image, take in how much is actually going on. There are various edges, shapes, textures, etc. that stack together to make various objects and the overall image we are looking at. At the start of a convolutional network, the types of kernels we use will be quite simple and more geometric, detecting things such as edges, corners, and simple shapes and patterns, like a circle, for instance. Additionally, each convolutional layer can have multiple kernels that produce multiple feature maps of their own. So for our example, we can see that our first layer has 6 kernels, and these kernels are detecting simple patterns like horizontal lines, vertical lines, and corners on our draw numbers. As a side note,
Do you see that they apply this filter on 7 would come up with this result? The other, and if I go to number, for instance, 2, the same, look at the output of the filter for 2, all the way 7.
the convolved pixels in our feature map, a nonlinearity function was also applied, in this instance a ReLU. We discussed this function in previous videos and the need for nonlinearity in neural networks, so our feature maps are more adaptable to real-world data. Also, you can now see how complicated this process would become if we had more than one channel, as each channel would have 6 feature maps, in this instance leading to 18 for an RGB image, and then those feature maps would have to be filtered together or operated on separately depending on your specifications. For instance, in a self-driving system, a red hexagon is a stop sign, so we would need separate channels and kernels for those channels. However, coming back to our example, just one channel, luminance, was more than enough. Moving on, now that we have a rectified feature maps, the next layer in CNNs after the convolution is the pooling layer. Pooling layers are used to downsample our feature maps, keeping the most important parts and discarding the rest, and primarily done to reduce the overfitting rate, and so that calculations can be sped up in later layers due to the reduced spatial size of the image.
Guys, do you see this? It's exactly the same real size of the pooling compared to the conv2D. Do you remember my critique about the previous video? This is solved in here. So, and when we have this 9, we have exactly the same 9 which is going to be more useful.
The type of pooling our network implements is max pooling, in which we take another kernel and slide it across our input feature maps, and the largest pixel value in that region is what is saved to our new output feature map. As you can see in this number classifier, the max pooled layer still retains the important information from the convolutional layer, while being smaller in spatial size. For instance, in this feature map, you can still make up the horizontal lines, and in this one, the vertical, from their respective original feature maps. So now, with the defining layers of the convolutional neural network understood, A, the convolutional layer which extracts features, and then B, the pooling layer which downsamples the feature maps, the next step is repeating these layers to build up more abstraction.
Okay, do you remember that I said if somebody asks you that what is the role of conv to the convolutional layers and max pooling, listen to this again, please.
Samples of feature maps. The next step is repeating these layers to build up more abstraction and convolutional neural network understood. A, the convolutional layer which extracts features, and then B, the pooling layer which downsamples the feature maps. The next step is repeating these layers to build up more abstraction in the network. As stated earlier, in later layers of the network, more complex kernels are incorporated that detect shapes, objects, and other complex structures, which is done by leveraging the previously generated feature maps and their detected simple features to build more complex ones. This
Let me just ask you one thing. What do you guess this high level kernel was supposed to do? Anybody has any idea? Sorry? Face recognition could be. What else? If that is a person or not, right? We had one data set very famous to distinguish between horses and human. Look at this. Yeah, we have ear, for example. Yes, here we have faces, but a person is Mahir. The problem of that is like a, what do we call it? A portrait, right? But what if we have a complete photo of a person who is standing looking 90 degrees to the cam? Is it possible by having this filter for those who are watching? I'm talking about this, the mouse is pointing to this. Is it possible to recognize a person which is like a portrait, or this person even, which we have just the upper body and we don't have any legs or something here? And the image that we want to recognize has a full body picture. Is it possible that this filter helps us to recognize that? Yes or no, you think? The chance is not that great because we don't have exactly the sieve that can help the picture go through, right? So what can we do to have the higher chance for that? What if I tell you that, Mayor, I'm going to just cut that part and maximize the size, zoom into that portion of the picture? You know what I'm saying? Or I zoom out, zoom in. Or what if a person you see here, a person in this filter is very much inclined towards right? What if a person into the left side? What if a person is very much in the center? You know what I'm saying? So these filters by themselves, they are not enough. What is your suggestion to, again, guys, remember computers are dumb creatures that they need to have lots of examples to understand. What can you do, Mahir? Any idea to help computer?
You know, like using formal max pooling
And after that, just keep that question till this moment. We have limited number. The limited number gives us how much accuracy? 70-some%. That's the problem. We want to increase that using a trick. We just want to see. I want you just to think about the problem. The answer is going to come down the road. Don't worry about that. Okay, let's just watch this.
is essentially the definition of abstraction. You can see in our example that in the next convolutional layer, there are 16 kernels, and these kernels are now much more complex. In the first convolutional layer, we were detecting simple edges and corners, and now, as you can see, horizontal and vertical edges are being combined, as well as other simple shapes from the previous feature maps. For instance, with this drawn 4, you can see this feature map combining both horizontal and vertical edges from various earlier layer feature maps, and resembling a bit of the structure of a 4, or with these feature maps of a 5, where diagonal lines and S-shaped patterns are.
Okay, Mahir, you might say that I can't see anything here. It doesn't matter, but if we give any picture that could make something similar to this set of things, means finding a part of the picture here, part of the picture in here, part of the picture in there, then computer is going to say, high probability is 5. You can look at it this way. I'm not saying it's an exact example, but you remember when we were kids, a few years ago, we played with jigsaw puzzles. Do you know jigsaw puzzles? That the different parts of a picture that we put them together and make one big picture. 1,000 jigsaw puzzle pieces, 2,000 jigsaw puzzle pieces, right? So imagine that we are going to cut it into split to different jigsaw puzzle pieces, and computer can scan and see, I can see that this should be, if I put them all together, this should shape a figure, that kind of thing. Does that make sense?
As you can see, similar higher level features are present for all numbers. Now, after this convolutional layer, just as before, there is another max pooling layer to reduce the spatial dimensions of the feature maps before the fully connected layers. As seen here, with these newly pooled maps, they look a lot more random to the human eye, since the spatial resolution is not very low. However, to a computer, they are just the key points in a matrix that represent a drawn number. You can also see now why we needed these pooling layers. From a raw input 32 by 32 pixel image with 1024 pixels and no discernible features, to 6 low-level feature maps size 14 by 14 pixels, resulting in 1176 pixels, and then finally 16 high-level feature maps of 5 by 5 pixels, resulting in 400 pixels. And this in general was the whole point of these convolutional and pooling layers, to detect high-level features with as low as possible spatial resolution, and why this part of the convolutional neural network is referred to as feature extraction. At this point, with the features extracted, we still need to be able to classify them, hence the second part of a convolutional network, the classifier. This part is comprised of fully connected layers, similar to a feed-forward network, except now our input to these perceptual layers are a high level of.
Okay, Nagin, that's the answer to your question. Do you see this? These are the results of all those conv max pooling things. We get to have lots of filters, right? The output feature maps. Now in this layer, what should I do? First, I should flatten it. And then this is going to be the input to the rest of the layers. In the example that we have in the book, we have just one hidden layer. What is the last layer? The output. And because we have 10 digits, we use softmax. Okay?
So it's like on the from and then flattening it and then.
Good point, you. So in some architectures, you can see that we have conv, again conv, then max pooling, conv, max pooling.
Depends on.
Yeah. And you know, there is no certain answer. You try this, you see, it works better. So let's keep that architecture, right? Try and error kind of.
Extracted features from our input rather than the raw input pixels. In this example's case, there are 120 neurones in the first fully connected layer and 100 in the second. And as you can see, these are sufficient to correctly classify numbers with a high degree of accuracy. Now, I hope you can recall, as we've covered in videos past, during the process of backpropagation and gradient descent, the weight and bias values are tuned as the network learns. In terms of convolutional networks, those values would still be altered during this process, and also other values, such as the kernel coefficients for convolution and pooling layers. Now, before continuing, I want to stop and highlight the fact that in our discussion of convolutional networks, we have made many generalizations and overlooked many details. For instance, hyperparameters like kernel size, stride and dilation rate, transpose convolutions and padding, different types of pooling layers, as well as other parameters and hyperparameters in our feature extracting layers and their effects on the output. Not to mention the impact of all the parameters in our fully connected layers, which we already mentioned in previous videos. If you want more information on these topics, check out the sources in the disclaimer and description below, as they are beyond the scope of this video. To move back on topic, throughout this video, we've now seen how and why convolutional networks excel at tasks related to image classification. However, where they don't perform well is for tasks such as natural language processing. This is because these tasks require memory, but not to fret. There are networks designed specifically for this, that among others will be discussed in the next video in the series. However, this doesn't mean you have to wait to learn more. If you want to learn more about deep learning, and I mean really learn about the field, from how these artificial learning algorithms are.
The rest is kind of advertising brilliant website, but I just want to tell something to you guys. You already have free access to LinkedIn's courses. Also, there are plenty of YouTube videos that they are YouTubers that they create tons of recent state-of-the-art content, mind-blowing. Apart from it, I by myself register, get myself to different classes. There's this one colleague that I have, and she said I spent something like 60 some for one of these websites. And I get myself to 2 courses every month. So if you look at this, there are tons of ways. Do not wait to just for a perfect time to start. Always try to learn something, and I have that discipline for myself. Always learn something new. And by saying that, guys, can you please give me a feedback? How much you could, how far you could get copying and so on. It should be dog, right? Copying dog. Or is it done? It should be almost at the end of it. Please check if it is done or not. Okay, to make sure that all of us could copy everything in the designated folders, let's have 10-minute break. So we are gonna continue at 1:45, okay? Hopefully by then, all of us, or those who copy the things, could have perfect folders. Is it working? So where are you in terms of which folder it's trying to finish? Dog validation or what?
Yeah.
Really? Can you see? Shows that how many times I suffered from copying and pasting. Okay, people at home, can you copy everything and everything works fine till this line? Thank you, Stefan. Okay. As I promised, let's start. It's 1:45. Look at this one. The book, we covered everything to have the foundations. We went to the building your network, and that is the place that we create all those conv2d max pooling things. You see that it says we have 32 channels, and then we have 64 channels, 128, and so on and so forth. Now we have better understanding what are those channels, and we say flatten, and then we have how many hidden layers we have here? Just one, right? 512 neurons in one hidden layer. And if you just say, show me the model's summary, it shows you everything. And if you multiply 7 by 7 by 128, it's going to give you that flattened number of neurons. And then we have density layers here. And that's it, the number of parameters, and we have and so on and so forth. And it says that we need to have optimizer because it's cat, dog, binary kind of thing. So the loss should be binary cross entropy. And the optimizer, we are going to use ramsprop, but we are going to define learning rate. The thing is, learning rate is kind of outdated. It's deprecated. And we need to say learning rate kind of thing. And metrics, we should say accuracy. So these are the changes that I have done. And you are going to see the model something like this. So, and in some cases, you see they update, for instance, Keras, but there is a kind of version incompatibility. So sometimes you need to get, for instance, layers from TensorFlow.keras, not directly from Keras. It could happen. I just left it here to tell you there might be occasions that you need to modify and get the answer like that. And this is the model that I created. And this is the summary. And I say from Keras import optimizer. And this is the legacy kind of thing that if you follow the book, it's going to give you this warning. It says that it is deprecated. And if you use learning rate instead, it is going to give you no warning. So now the model, the compile part of the model is defined. And now we get to data pre-processing, and let's see what are those parts. So look at this. It says whenever you deal with any form of convolutional neural nets that deal with pictures, for example, you need to have these 4 phases. First, you need to read the picture file and decode the JPEG into RGB layers, right? Pixels. You remember in the video, it says that each picture that we get, we are going to distinguish those actually channels and then converting into floating point tensors. So the next part would be converting everything, any array that we have, into a tensor, and then normalizing it. Like if the numbers are between 0 to 255, we are going to normalize it and bring it to a range of 0 to 1. Does that make sense? Right? So the good news is you don't need to do all those steps manually. You simply need to say, okay, Keras has utilities to take care of these steps automatically. And what is that? It is keras.preprocessing.image. If you say from keras.preprocessing.image import image data generator, this is a package which is going to take care of everything. Guys, the package would download everything, all the pictures, receive all the pictures, convert it to tensors, and then you can scale it to the size that you want, and then simply normalize it and so on. Look at here. We say from keras.preprocessing image, import image data generator. This is the first time that we learn something like generator. And the question is, what is generator? Anybody has any idea? Look at this one. I say image data generator and scale it down to the range of 0 to 1. Let's spend a few seconds, see what is happening in here. Whenever you say import data generator, you need to create an object. So train data gen and test data gen are two objects that you have created based on what? Based on the imported class. Guys, it is going to go to the train directory, and it is going to scale down the target size into 150 to 150. And the batch size would be 20. What's the meaning of batch size equal to 20, Rachel? Amount of pictures that we can pick in one shot, right? So get 20 picture, do the stuff, go to the next batch, get 20 picture, go to the next. How many cats and dogs did we have in train? 1,000 cats, 1,000 dogs totally. 2,000, right? Let me just show you some calculations. Okay. So how many cats and dogs we had? 2,000. What is the batch size here? 20 picture, right? The batch size. How many times should I go there and pick 20 pictures and come back to finish these 2,000? Can you tell me? It's not a trick question. 100 times we should go there. Every time that we pick 20 pictures, we are going to empty it after 100 rounds, right? So if one epoch goes through 2,000, in each epoch, we have to have 100 steps, right? To finish those 2,000. How many pictures we had for the test? 500 cats, 500 dogs, totally 1,000. Imagine that we have, again, 20. What's going to be this number? Simple, 50, right? So 50 steps we should go and get the 20, come back 20, 20, 20, 50 times. We're going to finish these 1,000. Does that make sense? Yep. Okay, look at this one. Here, we say that validation test data gen flow from the dictionary, and we say validation dictionary, right? If we go there it says change the size into 150, 150. So we scale the size in both of them. I'm sorry. We scale the size, huh? We go to the train, change the size of the pictures into 150 by 150. Every time take 20, and we know that the class mode is what? Cat and dog, binary. Does that make sense? Everything is fine. So what is the train generator? Train generator, imagine that we made a machine, that machine goes to the train directory and picks 20 pictures, scale them, and give it back to here, and goes back again and pick the next 20, and then the next 20. That's the machine that we created. Question, when this guy will stop? Sorry? After finishing the 2000 pictures, you think that this guy is going to stop? The problem is no. This is never-ending machine. This creature is not gonna stop. It goes to the first 20 picture out of 2000, second 20, third 20, and it goes to the last 20 picture. If you don't say, hey, enough, it is going to get back and pick the first 20 pictures again. So it's kind of never-ending loop. Okay, maybe you get a little bit surprised what is happening here, but for knowing that, we need to know a little bit about generator. I want you to spend a few seconds, and people at home as well, page 136. Can you please read page 136 and see what is happening? For the first time, we get to a concept called generator, and we see something new, which is yield. So any idea? Okay, let me ask you one thing. Imagine that instead of yield, we had return. Guys, simple question. Imagine that instead of yield, we had return I. And we call that generator once. What would be the output of this? Can you tell me? I is equal to 0 at the beginning. We say while true means non-stop, forever, run that. What is the value of I here, Rachel? 1. And then I say return, finish. The problem of return is it's going to terminate. It brings you back to the result, but it finishes. But yield means that, okay, keep that 1. I'm gonna go to the loop again. So it's like non-stop, gives you the result, and there is no end for it. So it's going to give you 1, 2, 3, 4, 5, 6, all the way to infinity. So yes, it's non-stop, and you have to say, hey, stop. And that, hey, stop is in here. Look at this one. I say for every item in generator, print the item, and if the item is greater than 4, stop. You see that? Okay, so if we go to this part, yep, there we go. It says that run this and it stops. If I say 40, it's going to run 40 times, right? 41, 1 to 41. Done? Yeah. Correct? And to understand this concept a bit more, because that is pretty much what shapes the next part of our challenge, would be this part.
In this final everybody, and this video will talk about generators. Earlier we only have talked about generators, and normally we use generators to bring or to fetch one value at a time. So let's say we have a list of values, there's 100 values, and if you want one by one value, what makes sense is to use generator. But there are small issues with generator, right? The first one, you need to get the generator where you have to define those two functions. Next and iter. We don't want to do that. We want Python to do it for us. And that's where Python says, okay, if you want iterators, we will give you generators. Okay, but now you will think we have to do two different concepts. But not exactly. Generators will give you iterators. Our job is done, right? So generator gives you iterator. So how exactly to create a generator? So let's do that. So what I will do is I will just jump to another file, which is gen.py, if you create your own file there. And here, let me define a function. That's right, we have to define a function on a class this time. So let's say our function is defined, and we'll do the same thing, we'll return the top 10 values. So let's say top 10, and this will return the top 10 value. And I will call this as well. So I will let me just say I have values, and this will be top 10. So top 10 is a function which will give you the iterator. But hold on, now a function cannot give you the iterator, right? A function has to be something special. So we have to convert this function into a generator. And the way to do that is, normally in function we write return, right? So if you say return 5, so this values will be having 5. But if you, instead of saying return 5, if you say int into 5, your job is done, because int is a keyword which will make your function as a generator. But now you will think, what's the difference? Even return will give you the value, even int will also give you the value. What I will do is I will just go back here, let me just print the value. And if you run this code, so you can see we got a different thing. Instead of getting a value 5, we got an object of generator. And that's the thing, because generator gives you an iterator. So this function is not a normal function. This is a generator because we are using int. Yes, if you say return here, then you can expect it to behave normally. It will return 5, but int will be different. It will also return the value, but it will return in the format of a iterator. And everyone knows if you want to find something for iterator, we have to use the next function. Let's run this code, and you can see we got 5. But now you will think, okay, that's fine. Even return gives the same output, right? There's a difference. Since it's a generator which will give you iterator, you can write multiple int statements. So let's say int 1. Then just copy this, let's do it for 4 times, and then you will be having different values here 2, 3, and 4. Now you can see we got 4 int, which is 1, 2, 3, 4. And if you run this code, you will only get the first value because you are saying next 20 once. So this is same as iterator where you are getting multiple values, right? So you got your own iterator without using next and iterator function. Let me do that one more time. I will say next. Yes, you can also say next, and in bracket you can say values. That's a choice you have. Otherwise, this will work. You can see we got 1, 2. In fact, we can also use a loop. So let's use a loop. I will say what I in vals, and then print I here. The moment you do that, you can see it will print all the values for you, remaining values, which is 3 and 4. This is how you can create generator just by using that one particular keyword, which is int. Okay, now there's another example we can take here. Example, let's say I want to print top 10 perfect square. You can do that. So let's create one. So what I will do is I will just remove this part, okay, because the logic will change. Everything else will remain same. Let me just not do this. Let's use a for to print all the values. But what should be the logic? So what I will do is I will say, I will take a variable which is I, so maybe n will do. N is equal to 1.
And now, since we want to print all the perfect square, we have to use a loop. I will not be using a for loop here because any type of for is a little better. Let's use while. So we say while and less than equal to 10 because we want to fetch top 10. And every time you find a new value, you have to just have to say int. You can say SQ is equal to n into n. That's how you find a square. Once you got the square, you can simply say int. And you can say SQ. Okay, so we are sending the value, right? So it is almost same as return, but then return will terminate the function, this will not. But that's something to remember. Now, once you say SQ, you have to say n, because you have to also iterate your n, right? You have to say n plus is equal to 1. I guess our job is done. This should work. Let's try. So I will just run this application. And you can see we got top 10 perfect square. We got 1, 4, 9, 16, 25. So that's how you can do it. Because this yield will give you the next value. Because see, when you say you're running a loop, you have this one value. So when you fetch the first value, this yield will return 1. When the loop says, hey, I want the next value, it will give you 4. When the loop will say, I want the next value, it will give you 9. So that's how you can iterator using a generator. But the question is, why someone will use a generator? Think about this. Let's say you are fetching 1,000 records from a database. So when you say you're fetching 1,000 records, maybe you want to print all, or maybe you want to process something from those records.
It's exactly the case that we have here. We have 2,000 photos and we don't want to bring all. We just want to get every 20 and do the job, right?
You want to fetch 1,000 records, all these 1,000 records will be loaded in your memory. We don't want that. Maybe you want to work with one value at a time. So there's 1,000 records, we want to work with one value at a time. In that case, you can use generator instead of fetching the entire list, you can fetch one by one value. So that's something you can do with generator. But that's maybe you can go as earlier example. So this is how we use generator with the help of English keyword. So I hope you enjoyed this video. Recommend the comment section and look.
Okay, so by saying that, now we know what is happening here. It's like something like return, but the return here is not going to terminate. So, okay, what about this? It says that we created a generator. We said train underscore data gen. This is something that we created, which is going to go, guys, we have a train directory. I want you to remember in home, sorry, collab chapter 5. And in this example, we have a train directory, right? What do we have inside train directory? We have 2 other folders, right? Cats and dogs. You don't need to tell that to this iterator. It is going to find out by itself and it goes inside it and say, I see you have to look at this one. Whenever you say, go to that train directory and you run it, it's going to tell you, I'm sorry, I need to run all this. Okay. It's going to tell you that I found 2,000 images belong to 2 classes. Isn't it beautiful? So the guy found that we have cat and dog folders, and I go through it and I found 2,000 different images. And if I do the same thing for the validation, look at the things that is happening here. It is going to find 1,500 into 2 classes, right? And now it's the time I told you, if you say, hey, go through the train generator, what is the problem of that? The train generator is a kind of non-stop loop that goes to the first 20 picture, the second 20 picture, the third 20 picture, and it goes all the way to the end, and it starts all over again. Let's just, for the sake of this example, let's go to a loop, and after the first iteration, let's stop it. We say for data batch and labels batch inside train generator. Just show me the data batch shape and show me the label batch shape. Look at the thing and just get outside the loop immediately. So we are not going to go through the loops. It says that, hey, I found 20 pictures. Each picture is 150 by 150. You remember cats and dogs pixels. We told generator to scale it to 150 to 150, right? And then we said we have 3 channels of color and we have 20 labels, well, 1 label for each picture. Does it make sense? So how about the next one? The next one is exactly the part that we have fit generator, guys. Fit generator is nothing but fit, which applies that never stopping machine that has generator. Means what? Means the responsibility of fit is finding relationship between inputs and outputs, right? Exactly, we have train generator. In each train generator, guys, what do we have? We have data and labels. Do you remember I told you we are gonna pick 20 pictures each time, and how many pictures we had? 2000. So 2000 divided by 20 pictures, it's going to give us 100 times we have to use it. This is what we manage by saying steps per epoch. Means use this, means stop after 100 times getting those 20 picture batches, right? How many epochs we want to go through? 30. You remember that we could say 10, 20, 30, 100, whatever. For the validation part, let me ask you, how many pictures we had? 1000. What is the batch size? 20. So how many steps should we go through? 50. And after that, we should stop. Is it clear? Okay, so please run that and let it go, because it takes something like half an hour, 40 minutes to finish. Even more. If you can use GPU, please use. I ran out of the GPU. Please start using it. Could you get there? So, is it working? Sorry? Yeah, or which epoch are you in? Sorry? Epoch 2. So the first epoch is crazy. It takes a lot of time, but the next epochs would be, but don't worry. The result would be pretty similar to the box result. Let's just go to the theory part while you're trying to finish. Okay. I quickly read this one because it is important. It says that let's look at the output of one of these generators. So we pick just one output. It says it yields batches of 150 RGB. So you see that 150 RGB that has come from there. Images, and the shape is 20, means that one batch of 20 pictures. And binary labels, well, definitely we are going to have binary labels 20, because for each picture we have one label. There are 20 samples in each batch, the batch size. Note that the generator yields these batches indefinitely, means that it goes forever. It loops endlessly over the images in the target folder. For this reason, you need to break the iteration loop at some point. And that at some point is something that we control by the steps. We're going to see that. Let's fit the model to the data using the generator. You do so using the fit generator method. The equivalent of fit for data generators like this one. Guys, it says here fit generator is exactly equivalent to fit while it goes forever. It expects, it expects as its first argument a Python generator that will yield batches of inputs and target indefinitely, like this one does. Because the data is begin generated endlessly, the Keras model needs to know how many samples to draw from the generator before declaring an epoch over. This is the role of the steps per epoch. So steps per epoch, after having drawn steps per epoch, batches from the generator, after having run for steps per epoch, gradient descent steps, the fitting process will go to the next epoch. In this case, batches are 20 samples, so it will take 100 batches until you see you target of 2000 samples. Guys, longest story short, it just wants to tell you this. Hey, 2000 pictures, batches of 20, 100 steps. And when using fit generator, you can pass a validation data argument, much as with the fit method. The difference is we have just 1000 images there. It's important to note that the argument is allowed to be a data generator, but it could also be a tuple of NumPy arrays. If you pass a generator as validation data, then this generator is expected to yield batches of validation data endlessly. Thus, you should also specify the validation steps argument, which tells the process how many batches to draw from validation generator for evaluation. So look at this one here. Now the history, we say model.fitGenerator. We say steps per epoch is 100 and validation steps is 50. And it's not gonna go more than once over each picture in each epoch because of those steps. This is the first time that we save the model. Guys, what is the model? Nothing but number of weights and biases that we have, connections that we have. Using it with H5 is kind of duplicated. And if you want to save it, it's going to give you this warning, duplicated. And it suggests to use Keras extension. So I just use both to show you. But I want you to analyze what is happening in the result that we get from, what do we call it? From this fitting mechanism. Just go a little and you see that this is the book's result, and my result is not very different from this. Let me just quickly show you the graph that I have. So you see the first one for the book is this one. The first one for me is this one. Not very much different. The first loss function graph is like this. For me, it is like this. Not very much different. It is different, but not very much the same tendency. Before getting to that part, actually, you have to change some of the stuff, otherwise it's not going to work. Like ACC should be accuracy, or val ACC should be val accuracy, and so on. So I modified the code, so yours should work without any problem. But the question is this: what can you infer from these things? Okay, look at this one. At the beginning, guys, what is the problem statement? Cat and dog. What is the chance of randomly you pick correct answer? 50%. Look at the result here. What is the accuracy? What is the accuracy here? So in the first two epoch, the validation is very much kind of disappointing, right? Which is 50%. But when we go further, we can find more better results, and it gets to something like 74. The books, guys, I got something like 78 as well. I got something like 71 as well. What is your result so far? You should be epoch number 7 or 8. What is your epoch number? For epoch 7, it is 70, right? 70 what? No, 71, 72, or 70. So you see that the numbers are almost in the same range. The thing is, if you see 74, we have it in epoch number 10 as well. And actually, I had a crazy good number, well, compared to them in epoch number 22, 75. But look at the result here. It shows that 8 and 10 are almost similar, but epoch number 22, you see that? It's a bit better. Which epoch do you think we should pick? What could be the best? This is the accuracy. We shouldn't very much rely on any of them. Look at this. Here is the loss. The loss has the minimum in epoch number 8. Then in epoch number 10, it is higher. And in epoch number 22, it is crazy. You see that? So based on that, we can infer that the best epoch number is 8. Does that make sense? Comparing all those two. And what can you infer from this? Whenever you have limited number of data, you immediately get to overfitting. Okay? So that is the major problem. So it says here in this part, it says that the plots are characteristics of overfitting. The training accuracy increases linearly over time until it reaches nearly 100%. And it is correct. Look at this one. For data in hand, you get to something like, hey, almost 100%. But is it real? Whereas the validation accuracy stalls at something between 70 to 70 some. The validation loss reaches its minimum after only, so that's what we checked secondly, right? After 5 epochs, for us it was 8. And then the stalls, whereas the training loss keeps decreasing linearly until it reaches nearly 0. Because you have relatively few training samples, overfitting will be your number one concern. You already know about a number of techniques like what we used, like dropout and weight decay or L2 regularization. We are now going to work with the new one, specific to computer vision and used almost universally when processing images with deep learning models, and that is nothing but data augmentation. So I read this sentence, and that's the last sentence that I read from the book today. But we are going to watch a video, and after that, we are going to spend time on assignment number 3. So it says that overfitting is caused by having too few samples to learn from. That's a question from the MCQs, right? Let's look at the last video. This gentleman, whenever you can find any video of him, don't hesitate to watch.
Hi, and welcome back to Machine Learning Foundations. I'm Lawrence Maroney, a host and guide, and I'm here to step you through the basics of machine learning from a coder's perspective. Over the last few videos, you've looked at convolutional neural networks and how they can be used for computer vision. You build classifiers for fashion, horses and humans, and cats and dogs. But one theme that was common was the concept of overfitting, where given limited data to train on, your neural network could get very good at recognizing this data that it was trained on, but not necessarily very good at recognizing any data that it had not previously seen. To help this make sense, consider this scenario. Say your whole life you had only ever seen shoes that look like these. Then to you, that's what shoes would look like. They'll cover the ankle, they'll have flat soles, they'll have laces, all those kind of things. So then if I showed you this picture, you'd instantly recognize everything here as a shoe. The big ones, the small ones, the ones on their sides, they're still in your mind shoes. But what if I show you this picture? Now we know this is a shoe because we've been exposed to shoes that look like this. But again, if all you had ever seen is the shoes I mentioned earlier, you wouldn't recognize this. There's no laces, the sole is all wrong, and it probably doesn't cover your ankle. You would then be overfit in the data that you think makes what a shoe is. The same happens with a neural network. If it hasn't been exposed to a labeled sample that looks like a high-heeled shoe, then it's the same as our hypothetical person who has only ever seen ankle boots shoes. Of course, if you don't have the data, you don't have the data. But there are many cases where a neural network overfits because of attributes in the image that it may not have previously seen. But using something called image augmentation, we might be able to fix this. This might seem a little vague, so let's show an example. On the left is a cat, and on the right is a person. Computer vision works by isolating features. So you might have features like the pointy ears at the top being indicative of the cat, or the 2 legs at the bottom being indicative of a human. But in the case of the cat, for example, the image on the right is a cat. You and I know that, but a computer may not. Because if it was only trained on images like the one on the left, then it's looking for triangular shapes oriented upwards near the top of the image, but the ears of the cat on the right don't look like that. So what if on our training set, we could rotate the images? So we train with a labeled image of a cat that looks like this. Then the ears are the same as the cat on the right. So by using a transform like a rotation, we're effectively creating new data to be able to train them. The good news is you have all the tools you need already to get started with this, using image augmentation to artificially extend your data sets to provide new information for the training of your neural network. And this can really help you with overfitting issues. To get started, you can use the image data generator. You've already seen this for image manipulation with the rescaling that you've been doing to normalize the image. And it supports more parameters, so let's explore some examples. So here's an extended image data generator constructor, where I've added a bunch more.
So you see that what I like very much is, you remember we had rescale, but we are going to have rotation range and width shift range and height. We have more parameters. There are just some of them. What does it mean, rotation range 40? Means that the cat could just go all the way to 40 degree this side and 40 degree this side, right? What's the meaning of shift range? Width and height. Means that the cat could go 20% this side, 20% this side. I mean, shifting this or in height, right? How about shear? Shear is the strangest thing, and it's not easy to grasp. It's like kind of stretching into Y dimension or X dimension. And then horizontal flip is, guys, this is this, but we have vertical flip as well. And then flip mode is nearest. What does it mean? When you shift towards left, there would be a space on the right side, right? Are you going to leave it blank? You can. But the other solution is you fill it with the nearest pixels to look natural, right? Look at the examples that we have here. Sorry. Look at the examples that we have. So here I rotated and, well, I didn't. These are the predefined filters. Oh, nice. Thank you, Stefan. Thanks for letting me know. So ended with good. Look at this one. We just, do you see that we rotated some degrees here, and this is going to fill this gap with the nearest pixels. How about this one? We rotated, and this one we just shift, or all these possible things that we did on one cat, right? So for the blank parts, we just use the nearest. We could leave it blank. I just wanted to show you that, and let's continue watching the.
That's the rescale one that you've already seen. You've already seen rotation range. This will randomly rotate each image by up to the parameterized amount plus or minus. So here you can see it's 40 degrees, so the image will be rotated left or right by that amount. Width and height shift range will move your image around in the frame by that amount. So here it can be moved by up to 20% in width or height, which can give an effect like this, where the image is width shifted and the subject moves to the left. Shearing can give an excellent effect if you set it up with this parameter. The value is from 0 to 1, so with 0.2 like this, you can shear by up to 20%. To see where it can be useful, consider these images. The image on the left is from the horses or humans data set, and the person is standing with his hands raised. The image on the right has nothing like it in the data set, and as such, it might fail to be classified as a human, or overfitted to standing poses, for example. But if the left image was sheared, it can suddenly look a lot more like the image on the right. The network, while being trained, could be trained to recognize an image like the one on the right, and will be no longer overfit just for standing poses. Another example is the zoom range. This parameter gives us a value from 0 to 1 to zoom by. This will give us a random zoom of 0 to 20% of the image size. Again, let's see an example of why this is useful. The image on the left here is a woman from the training set from Horses of Humans. The woman on the right is quite similar, but because of how the image is framed, we can't see her legs. And again, the neural network might be overfit to seeing full bodies that include legs. The lady on the right is obviously human, but the neural network may not recognize it. But if we were to zoom in on the image on the left, it now has far more similarities to the woman on the right, and we may be able to recognize the woman on the right as a human if we train with data like that on the left. Another example is horizontal flip. If this is set as true, then images will be randomly flipped. And let's take a look at an example of how this could be effective. The image on the left is from the Horses and Humans dataset. As you can see, she has her right hand up. The woman on the right is quite similar, but she has her left hand raised. If the training set only has images like the one on the left, we could overfit for humans with their left hand raised. But if we randomly flip, we could effectively extend our data set to include left hand raisers. Fill mode equals nearest is used to fill in parts of the image that could be lost in some operations like skewing. So that's a tour of some of the operations that are available with image augmentation, a really cool tool to help you avoid overfitting.
So we saw that one of the last thing was horizontal flip. Do we have vertical flip as well? We could have, right? But what if I use number 6 vertical flip? Is it going to help me? If I use 2, as in that case, 6 is going to flip and shows like what? 9, right? So this should be, these sets should be initialized thoughtfully. Means for MNIST, we shouldn't have vertical flip. Then it's going to destroy the chances of finding correct 6 and correct 9 in the digits, right?
Operations like skewing. So that's a tour of some of the operations that are available with image augmentation, a really cool tool to help you avoid overfitting in image-based datasets. But let's put it into action. Next, I'm going to show you a screencast of exploring image augmentation with a reduced version of the cats and dogs dataset that has only 2,000 images. And we'll see the impact.
So here's the cats versus dogs example. And what I'm going to do is use a filtered version of the data set that you can download from here that only has 2,000 images. Because it has less images, it's going to be more prone to overfitting. We'll take a look at the impact of using image augmentation on that overfitting. First of all, I'm going to create one that does not use image augmentation. So I'm just going to train the network with it. I'm going to use exactly the same parameters later on one that does use image augmentation so we can see how it works. So you can see here it's download.
There's just one thing. It is exactly all the steps that we have gone through this till this moment. And it's going to give us a kind of good heads up about what we're going to have next week.
It's setting everything. It's going to start training. It's going to train for 100 epochs. We can see the training is beginning now, and then I'll speed it up and see how it works later. Okay, now we can see that it has finished training, and the accuracy on the training set was 99.85%, so very, very high. But on the validation set, it's a bit lower at 75%. So that's clearly showing some kind of overfitting. Particularly, we're expecting that because we're using a smaller data set. If I plotted out the training versus validation accuracy, we can see that it actually flattened out around about 30 epochs. And the validation accuracy flattened out around the same. But you can see our loss drastically increasing on the validation set, clearly again showing that we're overfitting terribly. So what can we do about this? So one of the things that we spoke about in the video was the fact that we can do image augmentation. So here's an example of using the image data generator, rotation range up to 40 degrees in either direction, width and height shifting 20% in either direction, shearing 20%, zooming 20%, and then randomly horizontally flipping the image, just like we can see now. So let's now run the code. And this code is exactly the same with exactly the same model.
Except in this case, we're going to run the image data generator code to do the image augmentation. So if I start like this, it's downloaded the cats and dogs. It's giving us 2,000 images in 2 classes and 1,000 validation images, and it will start training. One thing you'll notice is that the training is a little bit slower this time because it's doing the image augmentation on the thousands of images. So while earlier, if I go back, you'll see our epochs were taking about 9 seconds. We'll see this time around, even though we have 100 epochs, it's the same, it's going to be a little bit slower. It's taking about 19 seconds. So we've about doubled the training time, a little bit over doubled the training time because of the fact that we're doing all of that image augmentation. So now, as we can see, we finished training. We ended up with 85% accuracy on the training set and 83% accuracy on the validation set. Now, while this may not look as good as your 99+% that you had earlier on, the point is here that it's not overfitting. We have 85% on training and 83% on validation data that I hadn't previously seen. So this model realistically is 85% accurate at predicting cats versus dogs. And when we look at our training and validation accuracy,
What can we infer from the result that the gentleman shows? You see 85, the accuracy that we have for the data in hand, and for unseen data, we have almost 83. What can we infer from that? First, the result jumped into 83 from 70 kind of thing, right? That's quite huge. But what else we can infer? The overfitting, the gap between validation and training is super low compared to previous that we had 100 while we had 70, right? Let's go to the next.
so this model realistically is 85% accurate at predicting cats versus dogs. And when we look at our training and validation accuracy, you can see the curves are fit together very nicely, and the training.
So it shows that they're very much close to each other, but can we make it even better? Let's see.
Validation also fit together quite nicely. Maybe here in some of the later epochs they're beginning to diverge, so that it's showing that it's beginning to overfit at that point, but we've probably overtrained the network at that point. In my body, like off about 60 epochs or something like that, so we can be sure. But again, this looks very, very nice now with the accuracy validation being very close to each other. We got that by using the image augmentation. Another little trick for avoiding overfitting is to add dropouts. Now, we didn't cover that in the video, so I'll just show a little sample of it here. But the only thing that I've done differently is I'm adding this dropout layer to the model after everything. And I'm going to be.
What was the range of dropout? We could have between 20% to 50%, but it goes to the aggressive kind of 0.5, the maximum.
That's dropping out. So in this case, it's to prevent what's called a proximity bias. When neurons are close to each other, can train very similar values. If you drop out a bunch of them, you can get rid of that, and again, you can prevent overfitting. So let's run this one, and it's going to do the same augmentation that we had earlier on. It's downloading the data and setting it down. It's going to start training it. So the training it may be a little bit slow. Let's take a look. Well, again, it's the same. It's about 19 seconds. So the dropout was impacting it anyway. But let's train this now for 100 epochs, and then after 100 epochs, we'll take a look at what the validation versus accuracy curves look like. Now that we finished recording, we're at about 82% accuracy and about a little over 82, almost 83% accuracy.
So you see here, we have a little bit of better accuracy in validation, right? But the beautiful part is that the gap between these two, and it's not necessary follow the same. I just want to go to, what is this minute? Sorry, give me a second. Yeah. So you see that, yeah, from that we got to, yes, 83, 85. But here we have kind of 2% gap between these two, with the expense of lowering down the accuracy. Look at here, we almost have way kind of lower in compared to the normal times. We have less overfitting, right? And even you can say in this specific line, we have underfitting, because the unseen data, validation data, provides better prediction for us compared to the data in hand. So is there any way that we can just get a better result and we have less overfitting as well? What do you think? You saw those two models, one with dropout, one without, and apparently this one shows almost no overfitting. Well, we have underfitting even. But can we just do something better? I'm not sure, but we have to try. In this example, we tried dropout 50%. What if we just do 20%? So it's going to be a compromise between those two. Maybe we get the benefit of two, and we have better accuracy and almost similar overfitting, underfitting kind of thing. We have to try. But anyway.
Be underfitting slightly. But again, the getting accuracy and validation accuracy as close as possible to each other is a sign of a pretty strong model. You can see we have that here. We're getting some wild swings here in the later epochs, and that's probably because of the dropout training a little bit too long. But again, using dropout by getting our accuracy and the validation accuracy closer to each other to avoid that kind of overfitting. Sometimes you can go too far, maybe underfit slightly. Not sure if that's the case here, because if you take a look at previous epochs, it's usually the training accuracy is a little bit higher than validation. So that's it. Those are some techniques, particularly augmentation, that will help you with fitting. I hope this has been useful for you. Here's the URL. Post.
Okay, so by saying that, we almost get to the end of the session for today, guys. People at home, thank you very much for participating. Malik, Nash, Stefan, and people here, thank you for being in the class. I'm gonna stop recording, and after that, we can spend time reading the assignment number 3 and see if there's any concern, any problem, anything. So have a wonderful one. See you soon.